Welcome to our fifth community call for VectisDAO. We have a very exciting course today. We are doing a demo of a proof of concept software stack for trusted crypto asset, part one, of two parts. And then also we are going through our Vectis wallet extension code and also our libraries for developers who are interested in integrating and working with the extension. Our extension has been approved on the Google App Store, so it's something that you could get on your browser as of now. So we're going to start with the trusted crypto asset part one of two parts. Today we are going to, well, let's go back to that. What is trusted crypto asset first? If for every transaction you have with a smart contract on chain, in our case, this could be a CW20 contract, you can attach a piece of data that contains the proof that you have satisfied certain compliant criteria. For example, you've been KYC'd, and this proof has been, you've been KYC'd and you hold this credential that satisfies this compliant criteria, then that means we don't need to exactly track like the wallets, because every single transaction will have a real life data attached, and then we can verify that on chain as well. So this is where on our diagram, this is a trusted crypto asset technical architecture diagram. You can find it on our GitHub. We're not going to go through actually the legal framework. That is also part of this document. We're just going to talk about the technical part. So on this diagram, you have on the right corner the holder of the asset and also the holder of verifiable credentials that has been issued to them by some issuers. And then they also control the Vectis wallet. And then whenever they want to transact with a smart contract on chain, they attach this piece of proof data. Today, however, we are going to directly go from the Vectis wallet to the VC verifier first, because there's actually a lot that is going on off-chain. And then in our next community call, we would show and demonstrate how to use this VC verifier in a dApp. And again, in this case, it's a CW20 contract, but you can imagine this could be basically any contract containing different business logics, including mixes. So if this piece of data that we are submitting on chain is also privacy preserving and also unlinkable, meaning that the issuer could not just track the chain and find out who or what verifier you've been interacting with, then this gives us a framework that is both compliant and private. So the solution that we're proposing here in this proof of concept is that we would be using here the on-chain verifier, and the credential type that we're verifying is a anonymous credential type. Couple of things: anonymous credential types supports revocation. Also, it is unlinkable, which means the credential that is signed by the issuer undergoes unblinding and then reblinding before going through the verifier. We have in this proposal, each holder would have at least two verifiable credential, of which they derive their proofs from. One would be the one from a trusted issuer, maybe some authority to say that you've been KYC'd. And a second is a self-issued credential. The reason why we have to have the self-issued credential in this case is that we are using linked secret, basically binding the KYC verifiable credential to the wallet address. So then people can't just go through the chain and then find these proofs and then go ahead and verify it, basically preventing Sybil attacks. So now we're going to see it all in action. We have a little demo for you. So we firstly need to connect to a wallet because we're submitting some transaction, and in this case we're connecting to our extension. We have, as I said before, there are two verifiable credentials. One is a self-issued one from the prover, and the other one is from the KYC issuer. Credential needs to be verified with something called a credential definition, which is basically a set of public keys that has been used, the corresponding private key has been used to sign different attributes in the credential. So here we'll get the prover's credential definition, and also we'll get the KYC issuer's credential definition. We could see, if we scroll down in the credential definition, a bunch of big number, but also under a part of it, we could see that wallet address is one of the attributes that needs to be in the credential, and then also the controller address. And then if we keep scrolling down there, we have the link secret, which is a piece of data that links the prover self-issued credential and the KYC issued credential. So we'll also go ahead and get the KYC issuer's credential definition, which has some sort of dummy attributes, including the name of the person, and also the link secret. So now that we have this credential definition from the prover, because, as I said, like these contains a public key that verifies the proof that we'll submit on chain. So we're going to have to put this onto the proxy wallet, our Vectis smart contract wallet contract. So go ahead, we'll upload it to the wallet. And because this account controls this wallet, we could successfully upload it. And now, so the proxy wallet contains this credential definition. So next step, what we need to do is, so these definitions basically are used to verify everyone. But now we need to do two things. We need to issue a credential for ourselves, and also issued one, and also request for one to be issued by the KYC issuer. Cool. So we'll go ahead and request that. So you can see that what has happened here is we have the first step, which was the credential request. What that means is, as a prover, we are blinding our link secret and then sending it over with the rest of the credential schema to request for a credential. And then the issuer would then basically populate these values. Let's say, my name, my age, etc. And then sign each of these attributes. And then finally, we process this signature that has been given to us, the holder, by the issuer, because the processing of this makes the proof unlinkable. So the prover now has a self-issued credential and also the KYC issued credential. Here we're just showing the different blinded secrets. So they're different for different issuers. So then even if the request is tracked, there is no linking between the two. Cool. So in the next step, now that we have these credentials, we need to generate the proof. Again, the proof is contains like zero knowledge proof of certain attributes and also predicates. So, for example, if the on-chain verifier requires you to be of a certain age, uh, maybe above the age of 18, then they could put that in the proof request. And then when you generate a proof, you would have to match that predicate so that you don't need to reveal everything on your credential, but you need to prove certain attributes satisfy this framework. In our proof, we have we derive it from two subproofs, and each of the subproofs are derived from our credentials. So here we'll create this proof. In the future, obviously, this is going to be done sort of all in the back, and the user wouldn't necessarily need to click through this. So here we have the proof, and then we are downloading it. It's a JSON file. Again, in the future, it could be something else. And then now finally, we have the proof, and also the nonce generating this proof is also in there. So now we are going to upload it and then send it to the on-chain verifier. So yeah, we have the proof here with all the known and attributes, and also the hidden attributes, and also the nonce. Then we'll send it to the on-chain verifier, which again, in next week's call, this will be a transaction done via a smart contract. So it will be done via a modified like CW20 contract. Yeah, and so here the proof has been verified. So this is the end of the on-chain verifier demo. We have updated our Vectis mains contract repo. It's a branch that is a working branch that contains like adding credential definition, etc. The actual VC verifier, it's still it's working in the background, but it's currently we'll need to clean it up before we open it up. And then that's it for me. So we'll do the Vectis extension library first, go through a deep dive how to use it, etc., and then we can take questions of both at the end. Thank you. Over to you, Javier.
Thank you, Belsi. An amazing presentation. Like Belsi said, I'm going through the code to explain the different parts of the extension and the core GS. We decide to separate the core because it can be reusable in other application. In this case, at the moment, we only use the core for the extension, but it's completely possible to use it in other application. So in the core, we have different folders. Uh, I see this folder kind of like modules. So each folder represents a module. These modules can be extended, and also we can create a new one. The most simple one is the key value store module. Um, we have an interface which we must follow in order to storage information in wherever it's in memory. For example, in the extension, we use the Chrome local storage. In other platform, could be anything, but just need to follow this interface. So we also have the memory key value store to in order to use it for testing purposes. And Yeah, that's pretty much the key value store. This is the simplest module. I think one of the most important one is the key ring. Um, uh, all almost all modules follow the same file structure. They have like a main file, a service, a handler, and a store. We will see that in detail. In this case, the main file, the keyring file, has all the logic of the wallet. It 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 does the serialization, the lock unlock process, save in the storage because we need to perceive the wallet, expose the key information in order to interact with the app. Um, the I think the one of the most important thing in this main file is all fields, all properties in the class are private. They are not accessible from outside, so we need the service in order to interact with the keyring. So that protect to the user for any attack. So in the service, we have different methods to interact with the key ring in order to lock, unlock, to get the status of the key ring if is unlocked, to restore the key ring when you initialize the core. There is a common method in all service, which is registering router. This method is necessary to register all message. These message are events, and these events uh, go to the server through the router. We will see the router in detail, but we use a handler to map this event in a specific method in the service. So when we register the handler, which is the keyring handler file, uh, we check the constructor name, and depending on the name, we call one method or another. We also include in this event message the different property they should have in order to make the the method works properly. So um, after that, I would like to show you the router to understand how it's managed. So we have the event router module, and in the event router module we have a file it's with the same name, and in this is a abstract class because we have the base for extend the functionality depending on the application. So we will see in the extension we have um, extension event router which extend from this abstract class. So the event router class use a message registry. The message registry is to register these types, these message types. The message type has the message. Sorry. The message has a type, and we use this type to store it in a map, the type like a key and the value like the class constructor. So when we send event, we we send the event serialized in a JSON binary. So when we transformate that events, this JSON binary don't have a prototype, so we need to build this event message with their own class, because the class has not all of them, but some of them has checkers to or protection to verify we have that property, or you are not you are not doing something wrong. So we also have the handler. So we register the handler we saw before. The root will be the key, and the handler will be this get handler in order to get the proper handler. Also, we have wars in case we want to protect in general the router with only for specific domains, in case we want to have a block list to prevent the user to be scammed. Um, and also we have the listen and unlisten method. This method are used to subscribe for event. You need to initialize the listen method in the router to listen for events. So the port, it's the name we are going to send in the event, so they can know where they have to go. So after that, we have the handler message. The handler message group all this method. As I said, it's parse the message with the JSON binary, and when we get the message, what is doing the message registry is to find the type, and when we have the event type, we assign the prototype. So after that, we check the root seed it is valid, and if it's valid seed, we get the handler, and we propagate that event to the handler, and the handler call the proper method service method. After the event router, I want to show some message as an example. For example, add mnemonic key. Add mnemonic key has the type. This is just an string. We can see here it's just an string. It has the necessary parameters to pass it to the service. In this case, the mnemonic string and the label for the wallet. Mm, um, okay, so we communicate with the core through event. So the we plan to send this event in a easy way. So instead of calling this event from every places, we create a file in each module, which is an store of that module. Um, the 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 store use a mob library in order to be reactive. So when you instantiate this store in a framework, front-end framework, or in JavaScript, it react to the chains. So when we trigger an action, we can know when the class has been updated, and we can get the refreshed values. So every store receives a message requester. The message requester is its responsibility is to send message to the router. So in this example, message requester is just an interface to send message, but in the extension itself, we will send you a extension message requester to request message to the router. We use generators to send to trigger this event instead of an async await, because we found this is the an useful way to handle reactivity with mobs. Yeah, we took that decision to use generators instead of async await. We have other modules like authorization, permission module. Uh, as I said, almost almost all of them follow the same file structure. It's not hard to follow when you understand the file structure and what does each file. Um, um, the authorization module is to wait for approvals when you need to sign a transaction or to ask for to uh, when a website asks for authorization to interact with your smart contract wallet, it has to be approved by the user. So we use this authorization service in the game ring and other areas like in the chain service when you add a chain to the a website to the wallet. Um, yeah, that's pretty much what the authorization service does. We have the same structure, the handlers. We have the store to trigger the event to the router, and also all the message. Um, we have the permission module. The permission module is for give permission to a website. So that website is allow currently it's used for website, but the idea is we can configure different permission, not just for website. It can not only this website it's allowed to interact with my wallet. You can configure maybe you can sign a transaction, or you can read my address and that kind of things. um, we have the service, we have the store to trigger the event to the router. We have the message. That's that is the all the logic in the core is related with these modules. we need to instantiate the core in the application. So we have this index file. This index file, what does, well, at first it needs to receive the Betty factory address, because we get information from the factory currently. Also it needs to receive a router, so it's agnostic of the platform. Sorry, it's agnostic of the application. It could be your own implementation. Also, the same for the approval requester. We have a library to track errors in the core. The store builder, which is the key value store implementation, so you can use wherever key value store you want. That is the all the core, and we are going to see the extension and see how can we use this abstract class and implement the own logic of the application. So we have the extension. It is the extension. We have like kind of the same structure. We have folder, which will, in my opinion, will be like modules, and the one module is the UI. I want to show you, for example, what we were talking about, the key value store. In the extension, we use the cron local storage, so we perceive the information there, and we follow the interface, the key value interface, to store its information in the extension. Um, I want to show the event router implementation. Like I said, one of the most important method in the router is the listen method, because that's what makes the router listen for events. In this case, the extension cron expose an API, and this API has an event listener for message. So we subscribe to message, and we call the on message handler in the event router in the abstract class. So for that reason, we extend from the event router. Mm, After that, we have the message requester, with his responsibilities to send message to the router. So again, the extension, we use the API exposed by Chrome to send message. We need to, because sometimes in the application we work with binary data, so we need to use that this library, which transfer this binary data in a string with a prefix. So the library knows how to encode and decode the payload. So the bands need to be a string. So for that reason, we lose the prototype, and we need to use the message register in the event router to recover the prototype. So it send a message, it wait for the response, and after that parse the response and return the result. In the authorization service in the extension, we use the API of Chrome to create a new pop-up, in this case will be to create a new pop-up, and we pass the information to that tab. We have different kind of pop-ups for example for signing, and another way to uh, for authorize a chain in the wallet. Mm, s- we also have this file outside the module, which are the main files for an extension. An extension, not all of them need the content script or the injection script, but if, for example, if you want to persist information in the background, you need you need the background. So in the background, we instantiate the router, the requester, and the store builder. This is just the Chrome key value store, and we call to the core start function, which was in the index, and we pass all the requirement params. We also have the content script. The content script is used for to inject the script, because in an extension it's not possible to interact with the DOM from a content script. For that reason, we use the content script to inject the injected script, which the injected script it used to expose the Vectis variable to the dApp. Mm, uh, After that, in the UI, we have w- I think the most important thing in the UI are the contests. We have a, a React contest. We use this React contest in order to instantiate all the store. So when the application is mounted, because in the extension the the background is mounted all the time, but the UI is not. You need to have the pop-up open to in order to have the UI running. If not, the UI it's off. So um, we have a core store class, which in the constructor instantiate all the store. We expose this core store in the React contest to interact from the components. We also instantiate an extension router and a message requester, because we need communication not only with the core, but also the core communicate with the UI. So for that reason, we also need to have a router in the UI, because when we ask for permission or authorization, we send that event is the core to the UI. So we have this provider in the app provider. An example of how to use this provider is, for example, in this component, we call the this function is kind of like a hook, which is a use contest of the core store contest, and we can destructurate the keyring store. After that, we can interact with the keyring store methods, and in this case, is for unlock the wallet. Um, we need to wrap all the component under this function. Observer function is another library for of mocks to interact to reactivity. So when something happen in the store, the UI is updated. Um, yeah, I think that's pretty much all of Betis. I know I've been running through all the code. And maybe I was a little bit fast, but is there any question about what I've been talking about? I'm open to suggestion and to improve the code or any doubt about the code. I'm happy to help and to try
Yeah.
to understand the code. So any doubts, I'm in the Discord, so I'm happy to help.